Jai Hind, welcome to class of Analog and Digital Communication. Today we are going to talk about delta modulation. So, delta modulation is a technique that will approximate my analog signal into a staircase representation, right? So, in previous lecture we have covered what is pulse code modulation and advanced versions of pulse code modulation like differential pulse code modulation, adaptive differential pulse code modulation. So, what is delta modulation? We simply can assume an analog wave, and when I represent it in staircase manner, that kind of representation, that kind of output wave, if we get from an analog signal, that kind of output is delta modulated output, right? So, why do we have to study, or why do we have to shift from PCM to delta modulation? Firstly, if we make our wave undergo pulse code modulation, then what will happen? There are three steps of pulse code to make a wave undergo pulse code modulation, that is sampling, quantization and encoding. And after following these three steps, I do get binary bits, right? So, a continuous in time and continuous in amplitude signal is finally converted into digital format using pulse code modulation, right? And we have seen the limitation of pulse code modulation, that the bandwidth required for pulse code modulation is too high. When the bandwidth required for pulse code modulation is too high, then we have to think of ways that will reduce the bandwidth requirement. So, delta modulation is one of such technique which will reduce the bandwidth requirement and will help me reduce the congestion. Let's talk about how. So, when I convert my analog signal into samples, corresponding to that those samples will get some quantized value, and corresponding to those quantized value will get binary bits, right? In case of PCM, if I do generate highly correlated samples to get better reconstruction of signal at the receiver end, then what will happen? Let's suppose corresponding to one sample I get 4 bits, right? So, for 10 samples totally I will be getting 40 bits, right? And now if I want to go for highly correlated sample, that will help me in better reconstruction of the signal. So, let's suppose the very same signal, instead of taking 10 samples, I'll convert it into 20 samples. So, how many bits now it will be converted into? Instead of 40, now 80 bits will be corresponding to that particular message. So, 80 bits corresponding to that particular message will help me retrieve back the message in the original form in a better way, in an accurate way, but it will do congestion, right? My bandwidth required for that will be too high. So, what is the solution for that? In delta modulation, what we do? We do sample signals at a rate much higher than Nyquist rate, but corresponding to each sample, we assume here 1 bit. And how do we do that? Using one quantization level only, that is corresponding to plus delta or minus delta, and corresponding to each sample I may get 1 bit. So, instead of 10 samples, now if I take 20 samples, the bits I will get is 20 instead of 80 bits, which I have taken example right away. So, let us see. When the sampling rate of a signal should be higher than the Nyquist rate, that is a well known fact, to achieve better sampling. If this sampling interval in differential PCM is reduced considerably, then sample to sample amplitude difference is very small, as if the difference is 1 bit quantization. Then the step size will be small, that is delta. This is what we use in delta modulation. So, this is one of the prominent feature of a delta modulator, that it uses a 1 bit quantizer. So, like the example I have taken, for corresponding to one sample, if 4 bits were to be generated, in delta modulation corresponding to one sample, only 1 bit will be generated, as it uses 1 bit quantizer. And a delay circuit along with 2 summer circuits, right? I'll show you the block diagram. Before that, delta modulation is a type of modulation where the sampling rate is much higher, and in which the step size after quantization is of a smaller value, which is delta. Such modulation is termed as delta modulation. This can also be called as a simpler form of DPCM, that is a 1-bit DPCM, right? Why do we have to go for differential PCM? So that we don't have to produce those many samples. With the help of the prediction circuit, we do predict the next sample. And but DPCM uses a usual quantizer, that could be a 4-bit quantizer or 8-bit quantizer. But if a DPCM is made to be 1-bit, to be using 1-bit quantizer, then that kind of modulation is called as delta modulation. Right? So delta modulation can be called as a simplified form of DPCM, as the sampling interval is reduced here and signal correlation will be higher. So this is my analog signal, and this is the staircase approximation of this analog signal. And if we read the staircase approximation, when it is increasing, that might be assumed bit 1, and when it is reducing, that might be assumed as bit 0, and likewise we can represent at the time of rise of signal, we can assume it bit 1, at the time of fall we can assume it bit 0. This is a mere representation, right? What are the basic features of a delta modulation? Here an oversampled input is taken to make full use of the signal correlation. We use oversampling. Second most prominent quality is we use 1-bit quantizer. Quantization signal is simple, we use 1-bit quantizer. This is one of the prominent feature of delta modulation. The input sequence is much higher than the Nyquist rate. As discussed, the quality is moderate. Design of the modulator and the demodulator is simple. Staircase, it is simply a staircase approximation of an analog signal, true. Step size is very small. So the prominent features that we must talk about is it uses oversampling, it uses 1-bit quantizer, and the step size is very small here, corresponding to plus and minus delta. So it involves simpler implementation. This is how my delta modulator block diagram looks like. In the input, I provide a signal, which is my xt. This is my analog signal. After passing it through a sampler, what do I get? I get XNTS, that is sampled version of my message, right? What I am focusing on here is the quantizer. So I am excluding the sampling part and the encoding part from this block diagram, right? So we assume what we get as input here is my sampled signal, which I represent by XNTS, right? With the help of summer circuit, I am representing along with this input, I give another input, which is the predicted, which is the output of the delay circuit. This could be considered as the predicted sample value. And what does the quantizer encode here? The quantizer does not encode here the complete sample, but the difference of the input and the predicted version, right? So my quantizer will only encode the error signal, which here is represented by EPNTS, which is summer output at quantizer input. Summer output and the quantizer input, true. Here EQNTS is my quantizer output, which can also be written as VNTS. And here UNTS is my input of the delay circuit, right? So what basically happens is, if I have this signal, I represent it with the present, the sample value taken here is compared with the previous sample, and if it happens to be a higher value, the step size will be raised by plus delta, right? It's raised by plus delta. It holds it for the sampling time. Then after TS time duration, after TS time duration, we again check for the input value, and if this input analog signal value is higher than the current sample value, what do? We raise the step size again by plus delta, and we keep doing it. For the very same reason, we can use a comparator as well, right, to which one of the input will be the analog signal. When it raises to plus delta, and we keep doing this at every TS duration. Now see here what happens. Here my analog signal has value which is smaller than the present sample here. So what do? We decrease the step size by minus delta, and we keep doing it, right? So such kind of representation I can provide to this analog signal. So we can see from here, to this analog input, this staircase kind of representation is the output for my delta modulated waveform, right? Although we do receive some noise here, which we discuss in the coming slides. Let's see what is the value of EPNTS here, as this is the difference signal, right? The error, which is also called as error signal. We name it equation 1. Now, what can I write as X cap NTS? What is this X cap NTS? This I get as summer output of what? Of the quantized value and the delayed signal. So this I can write as UN minus 1 TS, right? So this can be rewritten as this. And finally, what do we get as VNTS? That is my quantized signal, which is equals to EQNTS, and this represents the signum function, right? As it is a stair, we get pulse like representation, right? So my UNTS is this plus this, which is shown here from the circuit. Further, what is the value of my VNTS if I want to see? Here UNTS is X cap NTS plus EQ NTS, and X cap NTS is what? It's the previous value of my delay circuit, right? Previous value of my delay circuit, and EQ NTS is the quantized version of my error signal, right? Right? When these are summed, I do get output of my delta modulation. Now let's talk about how can we demodulate such signal. We can demodulate such signal with the help of delta modulator. The circuitry is simple. I know the delta demodulator comprises of a low pass filter, a summer and a delay circuit. The predictor circuit is eliminated here, and hence no assumed input is given to the demodulator, right? So these are my quantized output, which I do summation with the this delay circuit output, which I am representing by X bar NTS, and this output is passed through a low pass filter so that I can recover my low frequency message signal, which was my analog signal at the transmitter input. My V cap NTS is the input sample here, true. U cap NTS is the summer output. U cap NTS is the summer output, and X bar NTS is the delayed output. True. A binary sequence will be given here as an input to the demodulator, and the staircase approximated output is given to the low pass filter. What do I give input here is this, and to low pass filter such kind of input is given, and after smoothing it, my low pass filter will smooth out those abnormalities, and what do I get as an analog output at the delta demodulation. What are the advantages of DM over DPCM? It uses a 1-bit quantizer, which is a prominent feature. The designing is easier. However, there exists some noise in delta modulation. Here slope overload distortion is very small and granular noise is large. What are these kind of noises? Let's take a look. These are two major disadvantages of my delta modulation: slope overload distortion and granular or idle noise. Let's see what are these. We all know that in delta modulation, we approximate an analog signal into staircase representation, right? And we have to take care of one thing. If we are considering our audio signal, my audio signal is not a smooth kind of signal which has a uniform amplitude and frequency all the time. My audio signal in practicality will somehow look like this, with some sharp peaks and uh, these such kind of structure. In such case, if I choose a uniform step size quantizer, then such kind of quantizer will not approximate my signal in proper fashion, right? I'll get huge amount of noise here, right? So in such case, when the slope of my input signal is too high, that it is too large as compared to the step size delta, then I'm going to get such kind of noise which is called as slope overload distortion. So here I am representing my analog signal with xt, right? And I'm representing my staircase approximation with ut. What do I get? Step size is delta here, and my sample stays for ts duration. After every sampling time interval, I get another sample. So the noise that I get here because of steep curve of my, when the slope of my analog signal is too high, then the noise I get is called as slope overload distortion. And for such region where my step size plus this delta is too high as compared to rate of change of my analog signal, then the noise that I get is called as granular noise. So these are the limitations of my delta modulation, which causes distortion in the output signal. So what is the solution to it? So we cannot go with uniform step size. I have to choose a technique which will adapt itself and increase or decrease the step size as per the input message signal. Such kind of scheme is called as adaptive delta modulation. So what do we do in adaptive delta modulation? A larger step size is needed for the steep slope of the modulating signal, and a smaller step size is needed where the message has a small slope. That is the requirement. So let's make the step size adaptive. The minute details get missed in the process, so it would be better if you can control the adjustment of the step size according to our requirement in order to obtain the sampling in a desired fashion. This is the concept of adaptive delta modulation. Here the gain of the voltage controlled amplifier is adjusted by output signal from the sampler, and amplifier, we can use a voltage controlling amplifier for the same purpose, and this amplifier gain determines the step size, and both are proportional. So what does ADM does? It quantizes the difference between the value of the current sample and the predicted value of the next sample. True, it uses a variable step height to predict the next values. Although in delta modulation we adapt this, we do same thing at time of quantization, but the step size here is not plus minus delta, it is varied as per the input signal. So these are the references I have used. Thank you.